Chemists! So, today we want to talk about two things. One, we want to talk about the chemical energy required for bonds. Two, we're going to talk about the different types of energy we can use to break them down or create bonds. Mostly we're going to focus on breaking them down. First off, you need to remember that one, reactants on the left hand side of the equation, products are on the right hand. New compounds are formed by rearranging the atoms in molecules as opposed to creating new ones. Okay, stable compounds or elements may need energy to cause change. Okay, so to cause change, you might need to add some energy in. Because of this, chemical bonds can store energy. So in the example I like is photosynthesis. So when we add energy to carbon dioxide and water, light energy, it becomes sugar, and that stores energy that all other organisms get to eat and break down, and that's where our energy comes from. So, first we're going to talk about bond and lattice energies. In particular, the energy that's in covalent bonds and ionic lattices. So the energy that's holding them together. So chemical change, it often occurs through the release or absorption of energy, depending on the chemical reaction. Physical change breaks really weak intermolecular bonds, so bonds between the molecules. Whereas chemical change breaks or creates strong bonds between the atoms themselves, so inside the molecules. Intramolecular forces. Intermolecular, so between, intra, within. This means that covalent and ionic bonds are really strong. So energy required to break or create or cause a physical change is much lower, so it's less than the energy required for a chemical change. Alright, now if we go over here, we can see that ionic bonding is caused by electrostatic interaction between the positive and negative ions, and that's really strong. There's a lot of energy there between those. Whereas covalent is caused between the electrostatic attractive forces between the negative electrons and the nuclei that both share those electrons. If we look at energy per mole, kilojoules per mole of each type of bond, here we have the ionic ones are between 400 and 4000, and the covalent ones are between 150 and 1100 kilojoules per mole, which just means these ones are going to require less energy to break them apart compared to these ones. Alright. Alright, so let's do a quick bit of Greek. Lysis equals to break down. So if something says it's lithic or lysis, that means to break down. So a thermal decomposition is when we use heat energy, okay? So to break down the chemical bonds. A good example of this is iron oxide in a blast furnace. Now, just with the iron and the energy that goes into it, so we have iron oxide plus heat energy gives us a liquid ion and oxygen gas. Now that doesn't work in a blast furnace just like that. In a blast furnace we add coke, which is coal, and we heat it up by burning the coke, and this gives us iron 2 oxide. I don't know why that's a mistake, that C shouldn't have been there. So iron 2 oxide plus carbon monoxide, which is a product from the burning of the coke. They combine together, and this gives us a liquid iron plus carbon dioxide gas, and that's why they're not so great for the environment. Electrolytic or electrolysis decomposition. So we're using electrical energy here. When we want to extract some metals from their ore, the only type of energy we can use is electricity, and that's true with sodium and magnesium. The example we use for you guys, though, because it's one that you've seen before, is water. So if we pump electricity into water, in particular acidified water, we get hydrogen gas and oxygen. And then this leaves us with a very common day-to-day one, but probably a bit less obvious. And that is photolysis or photolytic decomposition. Now, this is using light, usually UV light, not always, to break chemical bonds. So some dyes in your clothes, they are light sensitive, and this is why we might have a t-shirt that's faded. So they spend the time hanging on the line, the direct sunlight, that fades them. Pharmaceuticals are light sensitive, not all of them, but some of them. And if you want to know if yours might be, have a look to see if they're stored in a dark glass jar. If they're in a dark glass container, they're probably photosensitive. Silver bromide is used in black and white photography on the film. Okay, so the shutter opens, light comes in, differing amounts depending on the picture it's seeing, where's darker, where's lighter. And it hits the solid silver bromide that's crystallized on the film. What it does then is the silver ions in that lattice, okay, all the electrons go back to where they belong, where they originally came from, and we get neutral silver atoms. And this creates a latent or reverse image. Okay, so if it's hit by the light in a particular spot, the atoms then leave where they are and get stuck, so the electrons leave, go back to their silver atoms, and we get a latent image. And this is the formula. So we've got silver bromide solid, gives you the metal, and bromine as a solid. Now, this light, what it's actually doing is it's breaking down the lattice and giving you the silver metal. Synthesis reaction. We're not going to spend too much time on this because you now have years of experience with this as a junior chemist. But often they require heat, and you'll think of this when you think of rate of reaction. Okay, so if we heat something up, it'll happen first, and that's because you happen faster. Sorry, and that's because you're putting more energy in there for the reaction to occur. So usually it's heat, but sometimes it's light or pressure, or sometimes electrical energy. And the example here we see in nature is lightning. Alright, so lightning comes down, zaps, and it can cause the oxygen molecules and the nitrogen molecules, which are very stable, to break apart and recombine and give us nitric oxide. Not so much a synthesis reaction as it is a breakdown and reformation. Oxygen will also break down and give you ozone, which is O3, in presence of electricity, and that's the burning air smell we get when anything electrical sort of short circuits. Alright, that's us for today. Hey, I hope you enjoyed today's chemistry. Bada bing, bada boom.